Part f is an example of another exponential function, but once again, it's a little bit different than the other exponential functions that we looked at. So you have to step back and say, how is this different? Well, back in D, we had exponential equals constant. That's not what we have here. Part E, we had exponential equals exponential. That's not what we have here either. So what's happening on this particular problem that makes it different than the others? Well, notice how many terms we have on this left-hand side. We have three terms. Term 1, term 2, term 3 on that left-hand side. And when you see that this is a three-termed piece on the left-hand side, that gives you a sense that it is a different kind of problem than the others, and it also gives you a hint of how to move forward with this problem. So thinking back to things that we've talked about previously in this course, we've seen this thing called quadratic in form. This is a problem that is quadratic in form. Now, if you don't remember how we played with quadratic in form, you might want to go ahead and pause the video at this point, go back, check out some of those quadratic in form problems, and then come back. So quadratic in form then has to have certain things in certain places in order to move forward. So we had to have three terms on the left-hand side. We have that. You have to have a 0 on the right-hand side. We have that. We had to have a constant term at the end. We have that. And we had to have something special in terms of the powers. The power over here has to be twice the power over here. We have that. So yes, this is quadratic in form. And because it's quadratic in form, we can use all those lovely quadratic in form ideas. Now, to help me out with this one, I'm going to go ahead and just change this first term just slightly so that it will allow me to move on to my next step a little bit easier. So I have 6 to the 2x power, but remember I can change that as 6 to the x power squared. If I have 6 to a power, all of that to another power, I multiply the exponents. 2 times x is 2x, so it's just a different way of writing down that 6 to the 2x. So I have 6 to the x squared minus 7 times 6 to the x plus 12 is equal to 0. Now, one of the techniques that we talked about in the quadratic in form world was the idea of using u substitution. So in that world of u substitution, I can come in and let u equal the piece that's hanging out to the second power here and to the first power in our middle term. Well, it's 6 to the x that's hanging out in both places. So I'm going to let u be 6 to the x. Now by doing that then, this 6 to the x is going to be replaced by u, and it was squared, so my u has to be squared. Then we have minus 7 times 6 to the x, but 6 to the x is u, plus 12 is equal to 0. Now by doing this, this looks a lot more familiar. This is a lovely quadratic equation. So again, lots of different techniques for solving quadratic equations. I'm going to use the zero factor property. So I want to find two numbers that will multiply together to give me a positive 12 and add together to give me a negative 7. A negative 4 and a negative 3 look like they're going to do that for me. So we have u minus 4 and u minus 3 as the factors. Now, to take each one of those and set them equal to 0 and solve, we get u is equal to 4 or u is equal to 3. Now, remember the warning that I gave you about u substitution. Anytime you use u substitution, you have to remember that you do the u substitution twice. So over here, I'm going to write down let u equal 6 to the x again. So what we have to do is take both of these pieces and move forward with this idea of bringing 6 to the x back. So instead of saying u is equal to 4, I know that u is the same as 6 to the x. So we have 6 to the x is equal to 4, or, and over here instead of u equals 3, I have 6 to the x. So it would be 6 to the x is equal to 3. Now, each one of those then is a nice, straightforward exponential equation where we have an exponential expression on the left-hand side and a constant on the right-hand side. We've already seen some of the problems like this on previous examples. So 6 to the x is equal to 4. The nicest, most straightforward way of solving that for x is to simply come in and rewrite this in terms of an equivalent logarithmic statement. So the equivalent logarithmic statement here, we're going to have log base 6 of 4 is equal to x. And over on the other side then, we're going to have log base 6 of 3 is equal to x. So now we have our two solutions. X is equal to log base 6 of 4, x is equal to log base 6 of 3. But remember once again that the author has requested that we find decimal approximations for each of these. And one more time we can go ahead and use the change of base formulas to make that happen. So I'm going to go ahead and write down the decimal approximations for each of those, and you can go ahead and check to make sure that you can get those same decimal approximations rounded to 3 decimal places. So log base 6 of 4 is approximately 0.774, and then log base 6 of 3 is approximately 0.613. So go ahead, pull out your calculator, double check to make sure that you can get those decimal approximations as well.